Okay, welcome back Science 10s. This is lesson 2.2 in chemistry, and today we're going to be looking at energy and mass. E equals mc squared may be one of the most famous equations in science. And it's not talked about in many basic science courses, but basically it means energy for E, mass for m, and c is the speed of light, which is really fast. It's the fastest anything can go. So this is explaining that mass and energy are related and that mass and energy can kind of go back and forth in between each other. And the speed of light part there, just really big numbers. So for simplicity, we can say that a really small mass multiplied by a really big number gives you a very big amount of energy. So a small amount of mass can produce a large amount of energy. Now, where you might see this chemical equation is in nuclear reactions in a power plant or in the chemical reactions that happen in the sun that are causing it to burn. And those are pretty big scale reactions where you have changes in mass with really big high energy reactions. And in these cases, a significant amount of mass is getting turned into energy. So technically, the mass in a chemical reaction doesn't necessarily stay the same. However, for the scale that we're going to be looking at chemical reactions and the type of reactions we're going to be looking at, mass in a chemical reaction is going to be conserved, which means that if we take the mass of all the products, that is going to equal the mass of all the reactants. So our mass can't go up or down during a chemical reaction. Basically, if we take 25 grams of this chemical and we add it to 25 grams of this chemical and it mixes together in a chemical reaction, so I put in different colors here, we get a new chemical, but it's going to have the combined mass of what reacted together. So it's going to be 50 grams. And although that makes a lot of sense, it doesn't always look that way. In this fire snake experiment by Science Buddies, it looks like mass is being created out of nowhere. It looks like this black stuff is just growing, coming out of thin air from the sand. And in this candle burning time-lapse video by Caspa22, it looks like the wax is just disappearing into nothing. But when we look closer at the chemical reactions, nothing is really being formed out of nothing or disappearing into nothing. Now, I'm not exactly sure what they used in that video to make that. However, there's a very similar experiment with sulfuric acid and sugar that creates a very similar result. So I'm just going to show the chemical reaction for that. And it looks complicated, but you just take sugar and react it with sulfuric acid. In this one, I think they're using some lighter fluid with some different type of sugar. But anyway, I'm going to look at this formula, which makes a very similar looking reaction. So we take the sugar and the sulfuric acid and it reacts to make carbon, which is what this is as well. It's just this big amount of ash, basically. And it looks like it's growing because it's full of a lot of air, because it also makes products of carbon dioxide, water vapor, and in this reaction, SO2 gas. Not sure if that's created in their video because they may be using things differently, and I know they're not using an acid. But the point is that we're making some gases over here, which is going to make the carbon full of air bubbles. And you might even be able to see there's a lot of circular kind of holes here from when it was formed around the releasing of gas. So it's making this really puffed up kind of ash that looks like it's growing, but really the amount of matter that was there at the start is the same that is there at the end. And if we look at the reaction in the candle, it's a bit simpler, but it's a pretty big formula for paraffin wax or candle wax. C25H52, so a whole bunch of C's and H's bonded together into that wax. But then when it burns, it just reacts with oxygen, and oxygen goes onto those H's to make H2O, and it goes onto the carbons to make CO2. So again, all the stuff over here is the same as all the stuff over here. It's just been rearranged. Why you can't see it is because, again, carbon dioxide is a gas, and like a gas you can't see, and water vapor is also a gas that you can't see. So when a candle burns away, all that mass and all of the weight of that candle has actually just gone into the air, and the air weighs that much more. To kind of keep track of that, we look at three different types of systems. So the first one is an open system, and you can see there's like an open container where mass can go in and out and energy can go in and out. So both can be exchanged. If we take that and we cover it up, so we make it sealed, there's a closed system, so I'm going to cover that up. That's when mass can't go in and out, but energy can still go in and out of the container. Think if like a candle was burning inside of a metal box, you could feel the heat on the metal box because the energy can still be transferred through that container. An isolated system is again where it's going to be covered and would be so well insulated that energy also can't escape. So matter and energy can both not be exchanged. This is mostly theoretical because even though we build like things like thermoses that try and keep all the energy in, we don't have something that can keep 100% of the energy energy in. It's all going to pass eventually through that material through heat transfer. So we don't really have a completely isolated system that we can make. I guess an example of one could be like the universe, because that's including everything, but we can't really build a 100% isolated system. A thermos is kind of getting towards the idea though, so you can maybe think of that when you think of an isolated system. So then if we have the candle experiment inside a closed system, I'm going to say this is a glass box, it's going to be a closed system, our mass should stay the same. So say we take the candle, we put it inside, and then we cover up the top so it is a closed system. Mass cannot get in or out. And we weigh it, and it weighs something like 6.52 kilograms. It'd be a pretty big candle, but maybe the glass container weighs some as well. But then we burn it, and then it's using up the oxygen, and it produces CO2 and H2O. You can see the candles got smaller, the wax seems to have disappeared, but all that mass has turned into CO2 and H2O, which was wax. And the mass, or the scale, should be still reading the exact same amount. It just turned from wax into CO2 and H2O. Next, we're going to talk about energy. Chemicals have energy. Just like in an energy drink, that chemical has energy stored inside of it. You can't really see chemical energy just by looking at it, but think of it kind of like a battery also that has energy stored inside of it that can do stuff. Or magnets that are going to be, if you're held close together, there's energy trying to push them apart. You can't necessarily see it, but there's energy there. And an analogy that I like to use, or a simplification, is thinking about how happy the atoms are to be bonded together. If they're happy to be next to each other, they are stable, or they are in a low amount of energy state. But if they don't want to be next to each other, they are unstable. They are not happy to be in that position, and it takes a lot of energy to keep them together. So there's a lot of energy keeping those things together. So that'd be a high energy chemical. So now imagine if we start with chemicals like this. Green does not want to be bonded to red, and blue does not want to be bonded to yellow. So these would be unstable or high energy chemicals. They have lots of energy stored within them. But then if we're going to allow them to react, which unstable chemicals would be more reactive, they're going to switch and they're going to pair up with whoever they want to be paired with more. So we react them and they move and they pair with people who they want to more, and they become much more happy in that state. When they do that, the energy gets released. The energy is now gone. Energy is given off, and they are now stable and in a low energy state. When we have a reaction that goes in this direction, it is called an exothermic reaction. You can think of exo as exit, because energy is leaving, it's exiting during the chemical reaction. And I put that in red because that's going to feel hot if you have one of those reactions, because energy is being released. This might be an explosion, there might be fire, or it might just warm up a little bit, but energy is a product. If we went back the other way and tried to force them back to be paired up with who they didn't want to be with, that would take energy, which is called endothermic. You can think of endo like into, because we have to put the energy back in to how it was before. So that's going to be cold because it is absorbing energy. So exo and endothermic reactions we have to know about. And that's it for this lesson, looking at energy and mass. So make sure you try the practice questions, ask me any questions in the live time, and I will see you in the next video.